Yeah, good afternoon, all of you. So instead of 2 o'clock, okay, now we are trying to have it a bit early. Okay, let us have a recap of the things, okay, what we have done yesterday, and then move forward and do some simulation, then try to understand, okay, how does the dimensions of the MOSFET will affect the transfer characteristics. Okay, let me see, okay, how many of us are there. Okay, now we have around 6 students. Okay, let us wait 1 or 2 minutes. Okay. Injare, why don't you come with me along? Okay, unmute yourself, Injare.
Yes, sir.
Yeah, fine. This is, of course, I have taken there are lots of PPTs available. So one of the PPT is for voltage transfer characteristics of CMOS inverter. If you can see, this is how the on x-axis you're going to have the output voltage V out, and then on y-axis you have the IDN, that is the drain current. What does this shows is this is for the PMOS. For the PMOS, can I write V in is equal to, okay, this is all related to PMOS, so let me just come to this bit later. Or can I say VGS of P is equal to, what is VGS of P here? Is it V in minus V in minus VDD?
Yes, sir.
So that's what is written here. So input is given by VDD minus VGS of P. Why this IDN is equal to minus of IDP? Because it is N and P, currents are flowing in the opposite direction. That's why ID of N is minus of IDP. What is VDS of P? Suppose if I share, okay, let us try to understand, okay, how they have written these two equations of V in and V out. So let me share the, what is that? My camera. How do I share the camera? Yes, okay, it's here. Sorry. So we have, all of you write the inverter circuit diagram. This is VDD, PMOS, NMOS. This is V in. This is V out. What is VGS of P? This is nothing but VG minus VS for P. So VG for P is V in and VS is VDD. So this is VGS of P. Naturally, V in is equal to VDD. Okay, what will be this? Is this plus VGS of P? Correct?
Sir.
Or am I correct? That's what is there here in this expression also. Okay, V in is minus of, is this fine, minus?
Yes, sir.
Okay, it's minus. And then how about V out? So what is V out of, can I write VDS of P is equal to VD minus VS. What is VD? VD is V out and VS is VDD. So it is VDS of P. Therefore, can I write V out is equal to VDS of P minus, can I write it so? Okay, is it fine? VD.
So with that VDD
Wait.
minus.
I'm just getting that. So they might have written something in the, what is that? Slide to trap us. I think both are plus plus no here. Is Vin is equal to VDD plus VGSP as per the equation. Let me just share this equation circuit with me. Where is my camera? Is this fine? I think this is plus only. Vin will come there. VGS. This is fine, no?
Yes, sir, plus.
This is also fine. Correct. Let us see what is there.
Yes,
Why, in the PPT it is not prepared by me. It is, of course, I just downloaded. So this is actually both a plus. This is also plus. That's also plus. So we try to understand, okay, how it is coming over there. Let us try to understand, okay, what is, okay, these two are plus plus. So shall I say this as the what output characteristics of PMOS transistor?
sir.
Correct this one.
Yes, sir.
Okay. Suppose if I flip this, will it go up? Can you
Yes, sir.
see that V in whenever it is whenever VGSP is minus 5 volt, or whenever the input voltage is 0, so does this minus 5, will it corresponds to 0 input voltage?
Yes, sir.
This is 0. So this plot, whatever you have, the bottom plot has gone up for this one. Is it correct?
Yes, sir.
Are these two same? How about this? Okay, VGSP is equal to minus 2. Is it for an input voltage of 3 volts?
3. Yes,
3.
sir.
White is flipped here. White is flipped. You can see it is flipped up.
Yes, sir.
It has flipped up because it is IDP. This is IDN because IDP is minus of IDN. Why these voltages have changed? Now I am representing VGSP and VGSP in terms of Vin. Correct?
Yes, sir.
Now instead of representing VDSP, I will represent in terms of Vout. Can you see now? Now to this each and every voltage, I will add VDD. So if I add VDD of 5 volt to this 0, what will happen to this point? Will it not shift to this point?
Yes, sir. Sir,
No.
but Vin is equal to VDD plus VGS now, sir.
What is Vin is equal to? Okay, let me
VDD
just
plus
come.
VGS.
1 second. Let me just go back to my circuit diagram and then show you what is happening. Okay, where is this? I'll take my camera. Okay. Now, let me just take only one graph. So this is for a voltage of VGS is equal to minus 5. Correct?
Yes,
Correct?
sir.
Is this VGS equal
Yes.
to minus 5? So when does your VGS is equal to minus 5? Here. This is 5 volt. When does this VGS is equal to minus 5? When Vin is 0.
Vin is 0. Yes,
Correct?
sir.
So
Yes,
can
sir.
I write this as equal to Vin equal to 0?
Yes, sir.
Correct? So when Vin equal to 3 volt, does my VGS of P is equal to minus 2 volt? When Vin is 3.
Yes, sir.
So I will flip this. So I will flip this because the currents are. So now this is corresponding to what? V in of 0. Correct?
Yes, sir.
For a V in of 0, whatever plot I have it here, I'm just simply flipped it and put it over here. And this is for V in of 3 volts. Correct?
Yes, sir.
Now this is VDS of P. VDSP is equal to 0 volt. Is it 0 volt now?
Yes, sir.
When it is 0 volt, how do I represent V out in terms of VDSP? This one. Is V out is equal to VDSP plus VDD?
Yes, sir.
I will transform all these points. These are all VDSPs. So I want to represent in terms of V out. So this 0 will become 5 because whatever voltage you have plus 5. So whatever point you have plus 5, whatever point you have plus 5. So will it now become something like this? That's what I have here. Can you see now? See this?
Yes, sir.
So this is the output characteristics of the PMOS transistor considering VDSP in terms of Vout and VGSP in terms of Vin. Correct? You can see they are not in terms of VGSPs and they are not in terms of VDSPs. They are in terms of Vin and Vout because I want to write the transfer characteristics.
Yes, sir.
So this has flipped here because ID of N is equal to negative of ID of P, and this has moved here because I want to represent VDS or Vout in terms of VDSP. Done? Hello. Because
Yes.
if I just show in my camera why we are doing this is where is that? Camera is okay. Because what is VGS of N? Is it not V in itself?
Yes, sir.
What is VDS of N? Is it not V out itself?
Yes, sir.
Since V in and V out are related to VGS and VDS of the NMOS transistor, I want to represent what is VGS and what is VDS of PMOS transistor also in terms of V in and V out. So that's what I'm doing here. I'm representing the transfer characteristics output characteristics of PMOS transistor also in terms of V in and V out. Correct? That's what
Yes,
being
sir.
done here. Now see in the next slide, just have a look at this. Can you see these graph? 1, 2, 3, of course. Can you see
Yes,
this
sir.
V in? Are they not the output characteristics of NMOS transistor?
Yes, sir.
The one which is going towards right side, increasing. So it's saturation.
Yes,
Can you
sir.
see the other one, the opposite one? Are they all for PMOS transistor?
Too much. Yes, sir.
Correct? Are you all getting?
Yes.
Can we
Yes,
just
sir.
okay? I think we can able to rewrite this. Of course, seeing wise, it looks very easy. When you start writing, you will of course we all will get okay. It is yes, correct. So what we'll do, we will write it for NMOS transistor. So this is NMOS transistor when VGS is 0, correct? Because MOSFET is off. When it is 1 volt, when it is 2 volt, when it is 3, okay 4, or when it is 5, correct? We are
Yes,
simply
sir.
writing it. Assume that this is 5. So when this is V in equal to maybe 1 volt, V in equal to 3 volt, V in equal to 4 volt, and V in is equal to 5 volt. Correct?
Yes, sir.
Similarly, when V in is equal to 0, what is VGS of P? Minus 5.
Yes, sir.
So you can see here, when V in is equal to 0, VGSP is minus 5. Will I write these characteristics now for V in equal to 0?
Yes, sir.
Of course, this is actually coming from this point. This is actually coming from here. So this is V in equal to 0. This has flipped there and it has moved here. Am I correct?
Yes, sir.
Similarly, write it for a different input voltage. It comes like this, and for next one, and for next, and of course this is for V in equal to 5. V in equal to 5. That's what is shown here. Can you see V in equal to 5? It is a flat line for PMOS.
Yes, sir.
Done.
Yes, sir.
So now from this we can able to understand when V in is equal to 0. Just here when V in is equal to 0, is my dot is here. That is what is the condition of this? Can you see maybe in the previous class we were just mentioning okay what are the condition of your NMOS and PMOS. This one, let me just share you this. Okay, this one we were writing, no, P is equal to n linear, N is off, and then this is linear, saturation, all these things. So that can be very clearly seen here. Is this input voltage 0 here? This one?
Yes, sir.
So when input voltage 0, you are on which part of your P characteristics? This is your P characteristics when Vin is equal to 0. Am I correct?
Yes, sir.
Just watch my cursor moving. Can you see? Is it exactly here? Is
Yes,
it
sir.
not the linear region of PMOS transistor?
Yes, sir.
And is the NMOS off? Because Vin is 0.
Yes, sir.
So that's
0.
why, as per our this one, so N is off, P is in linear region. Correct?
Yes, sir.
Getting confused? I think there is no confusion here.
No, sir.
So Vin is equal to 0 corresponds to VGS P is equal to minus 5, which is this graph. Since the VDS is 0, Vout is VS is Vout is 5 volt. See here? So
Yes,
this
sir.
is 5 volt now. So that's why NMOS transistor is in cutoff condition and PMOS is in linear. Suppose if you increase the voltage, does this input voltage reduce from minus
Yes, sir.
5 to uh,
-4.
minus 4, the
Yes, sir.
VGSP? Now you can trace this point. Can you trace this point? Can you see this dot line has moved up here?
Yes, sir.
But what is the region of operation of this curve which is rising here? What is the region?
Linear.
Linear. How about the this one? Can you see this, the one which is coming from the
Also.
bottom here? Is it now in saturation?
Yes, sir.
This corresponds to what? The horizontal line corresponds to which transistor?
NMOS.
So N is in saturation, P is in linear. That's what we wrote last class. See here? P is on, it is still in linear region. N is also on, it is now in saturation region. Correct?
Yes, sir.
Now let us go back to this slide again. If you further increase, can you say, of course, when I further increase means, okay, let me just make it somewhere here, maybe around 2.5 or 3 volts or 2.5 volts. What is this region of operation for both of them?
Saturation.
It is saturation. So that's why we wrote when the input voltage is somewhere in the middle, both are in saturation region. If it further increases, the one which was there in saturation will move into linear. So this is the linear region of which one?
NMOS.
NMOS. Saturation region of PMOS.
Yes, sir.
Correct? This is PMOS,
Yes,
no?
sir.
So the one which is coming flat here, this is PMOS. So that's why we wrote here it is both are on. Here what is the region of P here? P is in saturation, N is in
Saturation. Linear.
linear. Finally N will be in linear, P goes off.
Yes, sir.
P goes off. So that's what is. Can you see it is almost down here? So that corresponds to 0 horizontal line, which is a flat line for PMOS transistor, which is off. And this is when Vin is equal to 5. Can you see this is the one what we are referring to? The MOSFET NMOS transistor is in which region? Here.
Yes, sir.
Which region?
Sir, why the slope
Cut
is
off,
not
sir.
constant here?
Here, which slope? This slope.
Yes, sir. Both
Here,
of them.
lambda is non-zero. Lambda is non-zero. There is a channel length modulation. Correct? Tejas?
Yes, sir. Okay, sir.
If it is, if lambda is 0, it will flat.
Okay, sir.
Okay. This actually leads to something like this. Now there it was what ID and this one. What is that? V out. Now you are trying to write what is V out and V in. V out and V in. This is how it moves. You can see off. This is what off linear, and then it is somewhere here. It is one is linear. Both are saturation. This is what we discussed in the last class. This is how it comes. So maybe we'll also do a simulation of this and then try to identify. Okay, let me just show you the simulation. Is this visible? No, not yet visible. Let me just make it visible.
No, sir.
I'll make it visible. Share the content of this. Okay, now this is fine. Just note these things. Is it a inverter?
Yes, sir.
Don't say this is CMOS transistor with active load. So those days are gone where you're ending with active loads with N and PMOS as a transistor. You can see now I'm sweeping the voltage. Input voltage dot DC is done from 0 to 5 volt with an increment of 10 millivolt. Correct?
Yes, sir.
Just note down this Kp of NMOS is 200, Kp of PMOS is 100. That is mu n by mu p is 2. Correct? Here. What is Kp
Yes, sir.
expansion? Kp is mu n into Cox.
Yes, sir.
Okay. Why PMOS is half of that is we are assuming that the mobility of electrons or holes are half compared to mobility of electrons. Correct? If I
Yes, sir.
run it, see now I'm seeing the current as well as the output voltage. Let me change the color of this. Where is color? Color is this. Okay. Can somebody comment on this? Sirish.
Sir,
Yeah, comment on the current. I will take out this. Comment on the current. Why it is going like a pyramid. Can we relate this to something like this here? Sorry. Here. Can you relate?
yes, sir, but
How?
this is maintaining constant for some time, sir.
Where it is maintaining constant?
Like for
Which?
a very small time.
It's not time, it's voltage.
Yes, sir.
Here. What you're talking is this. Sirish, are you talking about this 0 to 0.5 volts? 0 to 0.5 volts?
Yes, sir.
And this 5 to 4.5?
Yes, sir.
Any reason from any one of you why it is flat here? Why it is flat? Okay, let me also show you what is this current I am showing. So this is the current that is flowing in the circuit. So this is the current what I am showing. The current is this from rail to rail, from VDD to ground. This is the current that is I am showing here. Correct? Now comment on this. Okay, why it is flat
Sir,
between 0 and 0.5 and 4.5 and 0. Yeah,
So because
sir,
of
this is the current.
0.5.
Gauri.
So threshold.
Yeah, because we know that this is a CMOS
Sir,
inverter. Yeah.
and also it is charging through P is this, sir. That is current passing through P is first rise, sir.
Mm.
Second fall is current discharging through N.
It is not current discharging. Of course, we are not talking in terms of charging and discharging at all because it is not with respect to time now. If it was there with
Okay,
respect to
sir.
time, it was been charging, discharging. Now it is not with respect to time. It is as the input voltage increases, as Gauri said, till 0.5 volt, NMOS is off. When NMOS is off, in the switch, in the series switch, when one of the switch is open, there is no current from VDD to ground. So that's why it is 0. From 0 to 0.5.
Okay.
Then from 4.5 to 5, PMOS is off. Correct. When PMOS is off between 4.5 and 5, again there is a switch open between that is from VDD to ground. So in these two extreme cases, current is 0. That's what is seen here. Can you see here at 0? Is it 0 current? It is till what point? Till what input voltage? 0.5. Here between 4.5 to 5 the current is 0. And after that, can you see initially when the input voltage is slightly increasing beyond 0.5, one of them is linear current and the other one is saturation current, but they are both of them are less. See the point here? This is less, no? Can you see this is increasing and it goes to peak and then again comes down? This is how the current is increasing and then coming down. So exactly that is what is in your simulation. Can you see the current is increasing here, which is off, which is on? This one 0 to 0.5.
PMOS is off.
No, N is off, P is on.
Yes, sir.
Okay, then one is in saturation, other is in linear. Correct? Here.
Sir.
Then
Yes, sir.
coming over here.
Both are in linear.
Here. At the peak, both are in saturation. That's what is this now. Here, this is the peak. This is half of input voltage, around 2.5. Can you see both of them are in saturation condition? Can you see these curves are meeting each other? Is it not?
Yes, sir.
So
Yes, sir.
this is 2.5. So at around 2.5 they'll meet somewhere here. Am I correct?
Yes, sir.
So and then it again reduces. So it is maximum current is flowing when both are in saturation condition. That too when the input voltage is exactly half of the VDD. Correct?
Yes, sir.
Shall we see the output now? How does the output looks like? This is the output characteristic. This is actual VTC. Let me take out the current. Let me take out, where is current? I will take out the current. I will change the color. Where is color of this? Okay, this is what we have seen. Okay, this is what we have written in the where is that? VTC. Correct? This is how it is flowing. Can you see that over here also again? Here it is maximum and then comes down. It will have a transition and then come down. This is still 0.5. It is full 5 volt. After 4.5 it is fully 0, and then here it is 1 is okay, both are on. Okay, extreme 0.5s, 1 is off. At all of the points, one of them is okay, both of them are on. Now the point is heard of what is that? Suppose if the, let me just what do you mean by logic high, logic low in your digital? What do you mean by, okay, assume that okay, 0 to VDD is 0 to 5 volt. What is logic 1? What is logic 0 in terms of voltage?
Logic 1 is 5 volts and 0
5
volts.
volt, 0 volt. Till what voltage you will consider it as logic high?
Will be cut off, sir.
No. Till what voltage you still, of course, if the input voltage is 3.2 volt, will you consider it as high or low?
No, sir.
Then what there should be some range, no? It is not only 5.
Yes, sir.
If it is
Yes, sir.
4.98,
Then
if it is 4.2, if it is 4.6, are they all logic high or logic? What is that logic?
Logic high,
there
sir.
will
Till what voltage? That's what we call it as noise margin and all other things. Correct? See now, shall I? Okay, I'll write a slope here. Whenever slope becomes 1, I will take this as VIH low. This is VI VIL maximum, VIH minimum. What is this VIH maximum, VIH minimum? Maximum, okay, this is 0 volt, no? This is VIL minimum. If the input voltage is from 0 to, assume that it is around 2.1 volt. From 0 to 2.1 volt, I can, okay, may not be 2.1, make it as 1.2 volt. From 0 to 1.2 volt, I will consider the input as logic 0 only. Getting the point? Because if the input voltage is between 0 to 1.2 volt, what is the output voltage you are getting? Is it not high?
Yes, sir.
So this is VDD. So we have a margin of noise. Assume that you have a signal and there is a noisy environment and you have an inverter. Assume that you have 0.2 volt or 0 volt. Whenever it is passing through this noisy environment, it has increased the voltage by 1 volt. So it has become 1 volt now. So now this is 0 volt, this has become 1 volt. Does this 1 volt will be still considered as logic low or logic high? That depends on what is the margin that you have made available for this. What is the margin for your low voltage now? It's almost 1.2 volt. Even if it is 0 volt, it is considered as logic low. Even if it is 1.2 volt, it is still considered as logic low. On the same lines, what is logic high? It is 5 volt. Assume that it is 3.2 volt. Any voltage between 3.2 to 5, you still consider it as logic high. So we were discussing now. You said okay, 1 is equal to 5, 0 is equal to 0 volt. If it is 0.8 volt, what is that? So unless you know what is the margin, you cannot say what is this. Since is this 0.2 volt coming within 1.2? Is it less than 1.2?
Yes, sir.
That's why you have a maximum limit for VIL. What is the maximum voltage that a voltage can take? You still consider it as logic low. You can see there is some minimum voltage. You cannot go below this. If you go below this, it is not guaranteed that it will be considered as low or high. But anything between 3.2 and 5 will be considered as logic high. Correct?
Yes, sir.
Getting the point? Okay, how does an inverter, how does the input voltage, can it be considered as logic low or logic high? Coming to this, where is that? This circuit, where is my circuit? I'll go here. Till what voltage you can treat this as logic low? Shall I treat somewhere here 1.2 volt here? Correct?
Yes, sir.
Even if I apply
Yes, sir.
1.2 volt or 1.4 volt, it will be still considered as logic low because output is high. Suppose if the input voltage is 2.2 volt, what is that? It's there in the transition point. It's there in the transition point. You cannot give that as an input voltage. So any voltage above VIL maximum and less than VIH minimum will not be a valid proper input. So we don't know, we cannot guarantee what the output would be. So output can be either high or either low. That depends on what is the previous condition. Even though it is not a storage element, so we don't know where it is going to settle down. Suppose if the input voltage is well within this range between VIL minimum, which is usually 0, to VIL max, which is decided by the dimension of the transistor. We will see how it will happen. So in this case, 0 to 1.2 is the range of input voltage which can be still considered as low voltage. And anything beyond, okay, let us see what is this voltage. Can you see it's almost somewhere around 3. Okay, here it is almost 3.5. Anything beyond 3.5, it's almost 0 volt. Of course, maybe here it is 0.2, 0.3, but it is fine. Is that correct?
Yes,
Can I
sir.
consider around 3.4? Any voltage beyond 3.4 till 5 volt will be considered as logic high.
Yes, sir.
Is that fine? Now, can I change this range? Can I make it equal to 0.8 volt or can I make it equal to 2 volt? Meaning, can I able to shift the dimension of the transition point. Transition point, can I just move it from 2.5 to somewhere else?
Sir, if the current curve should be steeper and steeper, then it would have been possible, sir.
Yeah, Tejas? Tejas, proceed.
Sir, if the current output current curve is there now, sir, it would if it is steeper and steeper, then it is possible to shift these VIL and
What do you
VIH,
mean
sir.
by steeper and steeper? How do I make it steeper? Here, current curve. Let me take the current. Sorry. What is steepness here? Oh, you want to make it rise fast? No, this rising fast I cannot make. This is my I'm linearly changing this. Of course, it is with an increment of 10 millivolt. I'm just keep on changing this. Now my point is, how do I modify this point? Instead of exactly 2.5, can I shift it? So you might have seen that the dimension of PMOS transistor is exactly twice that of dimension of NMOS transistor. Correct? So that's what we have maintained. If I show you the dimension, you can see this is W by L is 10, no? Hello?
Yes, sir.
And how much is this W by L? 5.
Yes, sir.
So I made it exactly twice because here it is twice. Correct?
Yes, sir.
Now just have a look at, I'll make this what? Maybe I'll make this also 50. Correct? Now what actually I have made here? Did I made PMOS weaker compared to NMOS? I have reduced the dimension. I have reduced the width.
Yes, sir.
Is it now become weaker?
Yes, sir. PMOS will do it.
PMOS has become weaker. If it has become weaker, what might can happen? Shall we just run it and see what happens to this one? Can you see now? Has it now shifted to left side?
Yes, sir.
Can you just make out why it is coming faster now? Okay, earlier this was there at 2.5. Can you see this was earlier here? It has shifted to left.
Sir, because before the current due to both are same, so I mean exactly opposite, sir. But now the current through the NMOS will be more
Okay,
than the current through the
let me
PMOS.
just also have a look at the magnitude of the current. So let me just go back here and then undo it. Where is that undo? Undo is here. Okay, it's here, undo here. How much is this? Okay, this is made 100. Let me just run it. Can you see the current is more? It's almost 2. Okay, let me just see the magnitude. It's 2 milliampere. So what I'll do, I will make this equal to 50, and then rerun it. Now the current has reduced. Okay. Other than current, it's IN is always equal to minus of IP. That is always there because you have only one current that is flowing. Whatever that is going down is actually the negative of the current which is going above. Correct?
Yes, sir.
Why is this actually shifted from 2.5 to this value?
Yes, sir.
Now what has actually happened now? Is this 1.2 volt, has it now reduced? Is your margin on the lower side, has it now reduced?
Sir,
Yes, sir.
because reducing the reduction in the resistance is happened there in PMOS.
No, that's what. Okay, what I mean to say is, has this come down like this now? Can you see this margin has reduced now? Am I correct?
Yes, sir. Yes, sir.
So this margin has reduced because NMOS has become weaker. Sorry, PMOS has become weaker. Am I correct?
Yes, sir.
So now if I do the opposite, what I'll do, I will make this 500. Instead of making this one weaker, I made this 2 stronger. Can you see now what happened? Can you see this has totally shifted?
Yes, sir.
Can you see whatever low noise margin, noise margin whenever the input voltage is low is more compared to noise margin when the input is high? Can
Yes,
you see
sir.
the margin is very little, whereas in this case margin is so much. But in an ideal case, whatever margin you have for the low should be same as that at the high, meaning this transition should exactly happen at mid of your VDD. So this, whatever, of course we call this as whenever the input voltage, at what input voltage output is also equal to, we call it as midpoint voltage. So now let me just do it for so there's the equation which we will derive in the next class. So we can does this shifting of plot, does it depend on the dimension?
Yes, sir.
Now it was earlier here at exactly midpoint 2.5, it was shifted to left side, now it is shifted to right side. I can able to shift it to any point depending on the dimension of the MOSFET, because there is no other variable available. Do you have anything other than the dimension for this transistor? Nothing. Of course, these are our input voltage which you don't have a control, because this is the input signal that is coming from external side, and this is supply voltage. Supply voltage you cannot tweak, and the input voltage you don't have any control. This is an independent parameter. If you want to have this to have a very good noise margin, this should have a transition point happening exactly at the midpoint of VDD. That is possible if the dimension of PMOS transistor is mu n by mu p times the dimension of NMOS transistor. What is the mu n by mu p ratio here?
2, sir.
2. So that's why I made it exactly equal to 2. It was the transition of your output from VDD to 0 was happening exactly at the midpoint of the halfway down the VDD. So this is exactly true even if I make it 1.8 volt and then sweep it from 0 to 1.8, and then of course you can make the dimension of this as still now 200, and then run now. Can you see now? It is the same type of transition happening. This is exactly middle. It will move to the right side if P is stronger. This will move to the left side if N is stronger or P is weaker. Correct? So
Yes, sir.
in that way we can able to play with the what is that, noise margin for both low input voltage or logic low and logic high. Okay. We will see in the next class exactly what is the derivation, okay, what is the equation that will going to govern the dimension, this midpoint voltage, where exactly this is going to have a transition from VDD to ground. Okay, fine, thank you.